going. Hopefully they'll join us. Um, so, hey, oh, yeah, why use Zoom over Blackboard? That's a whole other story. Um, there are a bunch of reasons for why to use Blackboard over Zoom, and there are reasons to use Zoom over Blackboard. Personal preference, yeah, there are a bunch of different things. Uh, there, let's talk about that after class. I still don't uh, have the quiz like ready to go, nor have I shared with you the material. So let's push that back. It's okay. We've got this one, we've got another one, and that's it. So there's lots of timing for it. Uh, yeah. Uh, do take a look at the homework. It's due Wednesday, but yeah, it's take a look at it. The next thing we're going to be doing after the homework will be our second exam, and I think before I assign that, I really ought to get you back the grade and the feedback on the first exam. So I will do that though. So what I'd like to do today is uh, is finish up a few of the remaining questions from that complex numbers practice sheet that we were doing last time. In part because they were there to make specific points. Some of them. The first parts were just kind of getting familiar with complex numbers, and then the rest, some of the other ones are there for specific points. So let's take a look at question number 6 from that sheet. And so hopefully you're opening up that sheet if you don't have, while you go, but I'll also write down what the questions are. Whoops, wrong thing. So let's do question number 6 from that sheet. And we're going to work through it, then we'll talk about why it's even here. So we've got two things, two different complex numbers. So they each have their own modulus and phase. So we got this one right here, Z, and W's got its own modulus and its own phase. Yep. And so it asks us to find the difference of the modulus squared of their sum versus the sum of their moduli. And so to make that a little bit clearer, we're looking for this. So add them first and then take the modulus versus take the modulus of each of them and add them, right? And we'll talk about why we're doing this in just a second. So let's just start off with the modulus squared. Right? The way we can write this is the product of the complex conjugate times the quantity. So, okay, not too bad. So let's write that all the way out. We can write this is this first term, Z. So the modulus is entirely real. And then this becomes e to the minus I theta for the complex conjugate. Oh, and what I should say is that the complex conjugate of the sum is equal to the sum of the complex conjugates. That was, I'm sort of skipping over that step right there. Oops, that's a straight line. All right, and what do we do with this? Let's just FOIL it out. We got the product of a pair of binomials. So for the first term, we get Z modulus times Z modulus. Sure, we get, whoops. I'm sorry, my pen's going crazy. Z modulus squared, and it's in e to the minus I theta times e to the plus I theta. That's just going to give us 1, right? And then let's do the last one. I'm going to do FOIL out of order, make it more of a FLOY. right? And again, e to the minus I theta times e to the minus I phi times e to the I phi is just equal to 1, right? And then we get so then now let's do outer C modulus times W modulus times e to the minus I theta times e to the I phi. And then for the inner, we're going to get the product of their moduli that. And so and these two are going to go away when we subtract off, when we take the difference that it's asking us for up here, third line down. All right, so this term right here, and so I'm going to write this, I'm going to rewrite the other terms. They both have a product of the moduli, Z modulus times W modulus, cool. And then we've got e to the I, and this, I made a mistake right here. On the last term, the products of the last, it should have been e to the minus I phi. So just notice right here, I had left off that minus sign there. So I'm going to write this out. So we've got an e to the, when we add these together, we'll have e to the I. On one side, we've got phi minus theta from the first term. And then from the second term, we'll have e to the I theta minus phi. So when we look at this, so first of all, we can see that when we actually take that difference, the difference right here, the first two terms are going to cancel out. That's common to both orders in which we do this. Let's examine this last term right here. This term right here. So I'm going to take this and write that up above and see if I can fit this all in one place. So here, I'm going to take this right here and go. Oh, and what was I doing with that? I'm taking just the term in the parentheses right here. Okay. So let me write this out in two different ways. I'm going to write this right here as e to the I. Notice that let's write the first term, phi. That's supposed to be a phi minus theta. And then the second term, I could just copy it over as it is. But if I factor out a minus sign from the parenthetical part of the exponent, it becomes e to the minus I phi phi minus theta. Exact same thing. So, and now this starts to look kind of familiar. This looks a lot like, so notice these two bits right here are complex conjugates of each other. So this right here turns out to be 2 times the real part. Because remember, the real part was the sum of the quantity plus its complex conjugate, but then you divide it by 2. So this is twice the real part of e to the I phi minus theta. I'll write this right here. I ran out of space. Let me just do that right here. And what is the real part of that right there? The real part of this is cosine of the parenthetical part. So this is equal to 2 times cosine of phi minus theta. Right? I could have just started out the very first line up here and written this as cosine plus I sine, and written this as cosine plus I sine of this. And notice when cosine of minus an argument doesn't change, cosine's an even function, but sine, when you put in a minus sign right there, the sign becomes negative, and it's because sine is an odd function, so that part would cancel when you added them together, and so you'd be left with the cosine terms. So what this is telling us now is, if we go back and take a look at this, right, when we add the two terms, and then take the modulus, in addition to getting the sum of the moduli, right, and the reason why I subtracted them off was to see what else we get. What else do we get besides the sum of the moduli? We get this term right here that will oscillate. The cosine term is going to oscillate, and it oscillates depending on the difference in phase between the two quantities right here. The other thing is, it's what was left, right, was modulus of z times modulus of w times this cosine, right? And so what this is right here, the reason I have this is, oh my goodness, what is the modulus? Give me 1 second. All right, that's going back a little bit. This is this. What is this right here? Is interference, right? So when there's it is indeed, right? So this is that it is, you know, and it's also like, if you take, this is why if you take two beams of light, even at the same frequency, right, and add them together, depending on whether they're in phase or out of phase, we will get this leftover term right here that will cosine, right, when it goes negative, can cancel out this part right here, right? So you can go from 0, because you've got, if z and w are the same size, you get 2z squared plus w squared. So let's call that, let's say the modulus of each of them is 1. So you get 1 plus 1, and then this term right here could vary from +2 to -2, right, if these are both 1 in my example. So you end up going from 0 to 4, right? You've got 1 plus 1 is 2 times 2 times 1 times 1. So you got 2 either -2 or up to +2. So you can get, you know, even though we've got this thing that is modulus squared, depending on the phase difference between them, we can get everything from 0 all the way up to something 4 times as big as one of them by itself, or twice as big as the combination of the two of them. So again, what was the modulus? Let's just go back and review that quickly. Just going to do this over here. Modulus. Couple things. So it is the square root of the real part of z, whole thing squared, plus the imaginary part of z, whole thing squared, right? Graphically, on our complex plane right here, if suppose that's z there, and this is our imaginary axis, here's my real axis, right? So the real component of z is this bit right there. The imaginary component of z is this bit right there. And the modulus is that length right there, right? So kind of like with a vector that was starting from the origin, right? We'd have an x component and a y component and a magnitude. The modulus is the analog of the magnitude, and the x and y components are analogous to the real and the imaginary parts. Another way to, cool, gotcha, yep. Another way to write that is here. We can also write it this way, that z modulus squared is equal to the complex conjugate times the original quantity. Remember, the complex conjugate, so you take the imaginary components and make them negative. Everywhere there's an I, you replace it with a minus I. So that was what I was doing in order to calculate this over here. We happy with that? Cool. Oh, so this is the new homework, right? Let me fix that. I think I didn't update that. I think the dates may be wrong on it too. I'll take a look at that. Questions. Let me just double check the instructions on the homework. For now, work on solving them. I'll update and make sure it's the LaTeX, not too bad. Let me take a snapshot of this, and we'll move on to the other problems, which aren't as long. So you can see that, right? The cool thing about this is it already captures the idea of interference, which is what we're going to want when we're dealing with waves. Give me 1 second. What was I was trying to save my snapshot. Are we using polar coordinates? Well, so for our polar coordinates, there are two ways. Remember, there are two ways we can visualize our complex numbers. And I'm going to erase this stuff right here, and we're going to draw this again. And so this is on that set of notes that is available for download under the resources, right? So on our in our complex plane right here, right? And if I pick here, let's call that point some complex number right there, right? We can write this in Cartesian coordinates, and that's the real of z right there, right? And that's, oops, the imaginary component of z. So we can say z is equal to a real part of z plus an imaginary part of z. So that's like Cartesian coordinates. But the same point, right? We can write the same point, in regular plotting that you've learned before. You could denote the same point in either Cartesian coordinates or polar coordinates. Same thing here, right? We can denote this same number with polar or Cartesian style. That's awful drawing. I'm trying to draw the radial vector there. And that radial vector is magnitude of z right there. And so we can write this as, modulus of z, e to the I. Let me redraw that thing, this axis again. Make z up here, z. This is the real part of z. That's the imaginary part of z. Gosh, it is hard to draw a straight line, apparently. Who did that? Who did that? There's my z. Who drew it better? There's my modulus of z, and right, we can say that right there, that phase, right? And so this is the polar coordinate way to denote it. So modulus and phase, or real and imaginary. Better? Okay. Cool. So let's do, we can skip over problem number 7. That's yeah, shows something else I need to know right here. You can think about that right here. Well, know what? Let me give you, I'll give you the punchline for 7 too, right? So Whoops. And so what do we do when I've got something like this? Someone got a suggestion. Take the derivative of this. Forget about it being complex numbers. So I've got a z star times a z times, I could call that a product maybe? Woohoo, product rule. Yeah, let's do that, right? I can write this right here. Yeah, we could do that right there, but I'm actually going to suggest let's do, right? So there are lots of different ways that we could do it, but one thing we can do right here is write this as like this. And that can be useful right here. And so that was the point of this. This is more relevant to quantum mechanics and stuff like that. But we'll see situations where we might want to do something like this too, because we're going to end up with a lot of times where we're dealing with things like our electric field. Yeah, and we'll see what that thing actually means in a moment, but modulus squared. And then if we want to do time derivative of it, then we might want to do something like this instead. Cool. Trying to do this way. Hello. All right, let's look at the next one. This one right here, right where we've got this alpha. Can I go back? No. Oh, well, I erased it too quickly. Camille, do you really want me to go back and explain something? All right. Are you sure? Okay. Yeah, I mean the idea was basically it was we applied the product rule. Take the modulus squared. We could write it as the complex conjugate times the original quantity, and then we can do the product rule on those two separate things. You're like, hey, wait, one z star, one z, isn't that the same thing? Well, not exactly, right? They're different quantities, so yeah, they're related to each other, but we can just, in a product rule, we don't really care, so we might as well use it. That was all. So here we've got this minus 0.1 plus 2 pi I, like that. And so the question is, what does the real part of e to the alpha x look like? Wow. All right. So how are we going to approach this? Well, I mean, we could write this out. Let's just do this. So I'm going to start, instead of writing real everywhere, I'm going to write just e to the alpha x, and then we'll take the real part at the end, right? E to the minus 0.1. Let's multiply it all the way out, x. So plus 2 pi x, and I'll put the I right there, right? It was 2 pi I times x, right? And at this point, like, well, okay, this looks kind of ugly, but we've got two different things, right? And this looks like a complex part, this looks like a real part. And so again, the beauty of exponents is we can do things like this, right? We know that a sum in the exponent is the same as a product of the exponentials. And now what do we do with this? Well, we've got this part right here. So we had a real exponential, and then we have an imaginary exponential. So, all right, this part right here we can write this as e to the minus 0.1 x times, right, e to the I something is cis of that something. So that is cosine of 2 pi x plus, I ran out of space, I sine of 2 pi x. Right? And so we take the real part of that. So whoop, real part of e to the alpha x. It's going to be the real part of that. Well, we're multiplying by a real exponential, so that doesn't change real versus imaginary. So real exponential times the real part still real, and the real exponential times the imaginary part is still imaginary. Yes, yeah, right. So just as a reminder, so e to the I theta is, we can call this cis of theta, right, which is stands for cosine time plus I sine. So cosine theta plus I sine theta. So here, right, we're saying theta is 2 pi x. That just happens to be what it is in this situation. So we can apply all that. So okay, what we're left with when we take the real part is just e to the minus 0.1 x times the cosine of 2 pi x. Okay, and so what does that look like? Can someone give me a description with words, say? You know what? All right. Sure. Harry, let's go ahead.
So it'll, because of the cosine term, we'll have some oscillating piece,
Okay.
but the amplitude of that is given by the e term. And because we've got that negative 0.1 times x, as x gets bigger and bigger, that term is going to get smaller and smaller. So we're going to start out with this really big amplitude that's then going to slowly trail off.
Yep, so we got a cosine that is oscillating, but getting smaller and smaller and smaller, right? So it's going to start out just like a cosine with, here's amplitude 1, and it's going to oscillate, looking good. Getting smaller and smaller. And I have it going really gradually. Right, so notice I didn't do the greatest job drawing it, but I tried to keep it so the period stayed the same. I think I didn't. And plus I got those couple weird squishy ones. Right. So one couple things. Yeah, you can't see when you're drawing. Thank you. Yeah. So I was going, doing it really, really slow and describing it, and you saw nothing. And then all of a sudden, there's the whole thing. Thanks for reminding me. I'm sorry. So you can see we've got this cosine that's going along, and it starts off with an amplitude of 1, and it's getting smaller and smaller, but it's a pretty gradual process as it gets smaller and smaller and smaller and smaller. And so actually I want to highlight one thing first before I do it, right? I could take a look at, well, where are these peaks right here, and just kind of go like this. And what this is right here, this line that connects my peaks right there, and it's not a line, it's a curve. Right, that curve is the e to the minus 0.1 x. And so I chose to draw it like this for a couple reasons. So first of all, we know that this right there, that's 1. That right there is 2 because it's each of the, I mean, it's cosine of 2 pi x. So it has a frequency, angular frequency of 2 pi. Angular frequency is 2 pi. And so that means that the period is going to be 2 pi over omega. So it's 2 pi over 2 pi is equal to 1. The period here is 1. So we're repeating every 1 as we go along. And if we look at it, what I was trying to draw, the 1 over e point, and again, e is 2.72, whatever, so a little bit bigger than a third. The 1 over e point, we reach that when this becomes e to the minus 1. So we reach that when x is equal to 10, so like out here. So I didn't do the greatest job, but 2, 3, 4, 5, 6, 7, 8, 9, 10, like right around here is when it's supposed to reach 1 over e. So that right there is supposed to be 1 over e. But anyways, when we have an exponential, the point of this right here is now we can see that our exponential, e to the alpha x right here, the real part will give us a real exponential, which will be a decaying curve like this one, or it could be one that's growing exponentially if it's a positive coefficient, positive constant. And then the imaginary part gives us an oscillation. So we can capture both behaviors, and what we're going to see is we're going to start out with things where they're either imaginary or either real, but pretty soon we're going to get into situations where we're mixing the imaginary and real together in our exponentials too, and in the exponents. Questions about that while I snapshot it? Give me a second. That the window's obscured while I'm taking the picture. Okay, what was that question? Oh, it was a thumbs up. All right, even better. So there's nothing wrong with questions. All right, so last little bit right here is question number 9. Number 9. So the question is, e to the ix, how do you visualize that? Right? So there are multiple ways to do this. And so one way to do this is recognize, hey, there is a real and imaginary part of this. So one way would be to take this and say, hey, we've got this thing right here, and this is my x right here. So I can plot, well, this is going to be equal to cosine of x plus I sine of x. So I can do cosine of x. So this is going to be the real part. And I could also do imaginary part and just show we've got both of these. We've got a sine and a cosine both present here. That's one way to do it. Let's take a look at another way to do it. Another way to do this is something that, oh, here we can do something else. I'm going to plot What do you think of that? It's true. The modulus of e to the I something real, right, is just going to be 1. Right? It's only if we've got a real exponent that the modulus changes. We could actually do this a little bit richer, though. What we can do is this. I'm going to draw over that line. This is supposed to be on top of that line. All right, so what's going on right there and here? I'm going to call that point right there. That's going to be my 2 pi. Right, and that right there is pi. Right, we can use something. We don't have to just talk about the position being the only way we can indicate value. We can indicate something like phase by using color. And then here's yet another one that we mentioned. Let's see if I can do a better job this time around. So it's going to start out perfectly real. Go. So I'm making a 3D plot. Again. So again, this is like a corkscrew. The radius of this, the radius from the x-axis in this case, right, is always going to be equal to 1, but it's going to wander around, circle around the complex plane like this. So basically, as x grows, we're just making a circle in this plane, but then that gets mapped out and turned into a corkscrew going around like that. So different ways to visualize this. Part of the problem is, right, we've got x, as x varies, we've got 2 things that change, the complex part and the real part. So we either have to show them separately, like in the upper left. We can show them together if we go into 3 dimensions, or we can show them together if we still have 1 dimension for the amplitude and then color for the phase. What do you think? Yawn, mind-blowing, somewhere in between? I'm going to have to take a look. I'm snapshotting this again right now. What did folks have to say? Yawn. Oh, carrot. I don't even know what a carrot is. Scary. It's scary because it's new and different, but it's scary because it's so powerful. Right? It's actually really, really useful. In all these ways, be useful in different ways to do these things. Unlimited power. So in some ways, this is the story of the way physics and math interacts. It's math. We develop math to describe stuff, and you can start off with very simple, concrete things like counting numbers and how you combine them and add them up and stuff like that. And then we can move into and that describes just the stuff that's in front of you. But then you can get a little bit more abstract, a little bit more difficult math, but it can describe a little bit more things. And then we can get more abstract, and it will encompass multiple different regimes that before were separate. And now this one big but more complicated, more difficult description describes all of it. So it's getting more and more abstract, right? We're talking about these multidimensional things in order to represent complex numbers, but it can allow us to do so much more. And you notice that I describe math in purely utilitarian, serving type terms, which some mathematicians might object to. So let's actually take this and bring it back to our idea of waves. All right, so we're going to come back. We're not using our pen right. We were talking before. Oh, I'm in black now still. All right, let's go with it. Who likes black? Who likes blue for your favorite colors? I'm not going to do yellow. That's hard to see. All right, so before we were saying it was A cosine, and we of kz minus omega t plus delta, right? So we can write that. If we look at that, that looks like, hey, this is the real part of A times cosine, so long as A is real, of, oops, not cosine. That's the whole point of this all. Right, this is the point where we were. This looks like something we did in Fund 3. I'm wondering what part in Fund 3. But yeah, that we should be, we're going to start making connections to a bunch of different classes. I'm just trying to see specifically for that. But yeah, we'll come to it. Oh, I'm holding down a button. All right, and so what if we're going to do this, then hey, if we've got this A times the exponential, like we can actually just start working with that thing right there, right? So with this bit right here. So let's call, that looks like f, our function, but it's not quite. It's a complex version of it. So we're going to define that to be this thing right here, A u to the I. Right. So remember, A appears an element. So what does that mean right here? That amplitude. So right, A is an element of the reals, is what I was writing up there. A is real. So we've written this out like this, and it turns out, well, okay, that's fine, but I can also write this out and we can get the oscillatory bit, right? This part right here oscillates. It oscillates if you change z, it's going to oscillate, or if you hold z constant and you change t, it'll oscillate. And then we also have this other phase shift, but that's something separate right there, right? And so I can write this again and just capture the oscillatory part. And what I'm doing is I'm folding that phase constant, the e to the I delta is the phase factor. We're folding that in to my complex amplitude. Right, so this, the wiggle on top is called a tilde. So, but I'm often going to read this as, as something like the complex A, complex amplitude, or A complex, or I might say A tilde. But rather than naming the typesetting feature, I'd rather actually describe what it's talking about. Oh, but just a hint, LaTeX. Suppose I want to do that. Right? In order to do that, I do \tilde A. If you do that in LaTeX and you get like your tilde looks too skinny, whoops, we lost Camille. You can also do \wide tilde, all one word, 2 words squished into one, and that makes it so you don't get this little skinny tilde sitting on top of the letter. You get something that's about as wide as the letter. Cool. All right. So again, here we'll just say that's our complex amplitude. All right. So when we did all this stuff, we motivated. Yeah, Nate. I think you're muted if you're talking. Can't hear you. Are you talking, Nate? Hello. See you pointing, but I can't hear anything. You're talking, but we're not hearing. I see you. Hey, Nate, it shows that you're talking, but we're not getting any sound. Yeah. Oh, yes. Yeah. I see what Nate is asking. Yeah, I left something out. Brr. Here, let's see if I can I take this and drag this over? No. Oh, wow. I just did something crazy. It's out of control. Yeah, absolutely. What it was supposed to be, this A tilde was supposed to be the combination of my real amplitude times that phase factor with the phase constant. Thank you very much. My bad. Here, we'll erase this. All right. Thanks for catching that. That would have been bad. Let's see. Want to go crowded? I'm gonna snapshot this. Give me one moment. Okay, sorry that's so slow, but this way we have access to in the future. So we got this right here. So we'd motivated this initially, like just before we took this digression to study complex numbers, we looked at, well, what happens, suppose we want to add together these two things that have the same wave number and frequency, but they've got different amplitudes, cosine. Oh, and they also have different phase constants. Right, and so doing it with cosines was going to be kind of hard, and if we wanted to really, really simplify it, group stuff together, we were going to have to do all kinds of trig identities and stuff like that. But working with complex numbers, things can get a little bit easier, right? Because those are two functions, f1 and f2, right, are the real parts of the complex functions. Complex f1 and complex f2. Okay, and adding together real things, we don't change their realness if we add them together first. Right. Oh, and in the end, right, that looks like our complex fnet. So let's dig down and take a look at that complex fnet. So, all right, I'm going to write in my complex f1 and complex f2. So that's going to be a1, Camille's coming back, a1 complex, right? And we'll have e to the I kz minus omega t, right? And then over here, complex amplitude. Oh, sorry. See what we did right there? Wait a second, didn't I leave something out here? Am I missing something here for my f1 and f2? Like, wait a second, he's got kz minus omega t plus delta 1 and plus delta 2. Where did those deltas go? Oh, right here. Right? Remember, our complex amplitude contains the real amplitude, but also times the e to the I delta. The phase constant is folded into this complex amplitudes right here. So I can take these things right here now, and notice now we've got a common factor of e to the I kz minus omega t. So I can just group this together, right, and say, write this as a1 tilde plus a2 tilde times e to the I kz minus omega t. Or another way to write this is I could call this a net tilde. Right? And in particular, like, right, we take a look at this. Let's take a look at, so rather than having to do trig identities and stuff like that, by working with our complex functions and their complex amplitudes, we are able to turn this, take the oscillatory terms that are in common with them and factor it out. And then all the addition comes in with the complex amplitude. And the oscillatory part, the part that may turned it into a trig nightmare, that becomes something else. That's just simple addition, or actually a common factor. So just to summarize, though, what was going on over there, my A net complex, right, was equal to A1 complex plus A2 complex, right? And we can expand those out. A1 complex is A1 times e to the I delta 1, and the complex amplitude 2. Oh, no, sorry, I don't want that. Is equal to the real amplitude times the phase constant. All right, and then, oh man, this took a lot longer than expected. And then all that right there is, we're calling that real Right, and notice these are complex numbers right here. So I could make a graph if I wanted to, right, with these things. And where I've got the imaginary axis and the real axis, right? And A1 is going to have some modulus and some phase factor. And A2 will have some other modulus and some other phase factor. Right? So I can just do addition in the complex plane like that. Does that look kind of familiar? Does that look like something we've seen before? That drawing there? Fraction. Oh, you're getting too far ahead. You're thinking too physicsy. Think like early on in fun. Yikes! 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 Yes, that's okay. So we're just trying to add up these things, right? Generic vector addition. Yeah, right. We basically we can use the same kind of math that we did for vector addition, right? We've got a magnitude, in this case, a modulus, and a direction. In this case, the phase angle. Magnitude. Oh, I'm pointing with the wrong thing. Modulus is like the magnitude. Phase constant, like the is like the angle, the direction. Then add on something that's got a different magnitude and a different direction, a different phase. Right? So we can use the exact same math, and you can break it up into real and imaginary parts, just like you break up vector addition into x and y parts. And then in the end, all this stuff right there, after all this, our net function is going to be the real part of the complex net function right there. And so after all that, it's just my a net right there times cosine of kz minus omega t plus delta net. Right? But we can use that stuff over there. Right? We can get for the amplitude and the phase constant, we can get that from doing math over there, right? Using basically the tools of vector addition. And that's something you do in your homework, in the next homework set, I think, if I remember correctly. So let me snapshot this, and we've got, what, 10 minutes left to look at something. Okay, cool. All right, so we did this right here. We're adding two things that are two functions, two different waves in this case that were both sinusoids, and they had the same wave vector, same frequency. The only thing that differed was their amplitude and their phase constant. But we've also talked about having like arbitrary wave packets, right? Arbitrary waveforms. It could just be that Gaussian that was sliding along, or it could be something else. It could be we might just have like a kind of a couple wiggles and then they travel along. So how do you make up waves that are have these arbitrary shapes? And so there's a tool for that, right? We know that any one of those, we know that first of all these sinusoidal terms are solutions to the wave equation. We also said that linear combinations are also possible, right? If you've got multiple solutions to the wave equation, then linear combinations of them will also be possible. So it turns out right, we can use these linear combinations to make these arbitrary waveforms. And the tool for doing it is called Fourier transform. And you saw kind of a premonition of this, perhaps, when you were doing separation of variables in chapter 3, and you found places where there are actually multiple different solutions that that would work. And in fact, you had a whole series of solutions that would work, but the boundary conditions made it so that only certain terms fit, and you did Fourier's trick to pick out the right terms. I don't know if that sounds at all familiar. The silence is deafening. So yeah, familiar. It was kind of and you're like, this is really complicated and really ugly, right? And actually, just before I go too much farther with this, if you remember, in some of those boundary condition solutions, right, we had, you had these boundary conditions, separation of variables, and Laplace's equations, and it turned out for some of them, right, you got things oftentimes that look like exponentials, and other times you got oscillating like cosines or sines, right? And the reason why you got both those, right, is you could have the second derivative was either equal to some factor, time equal to, call it k squared, some constant squared times the function, or you had the second derivative, Laplace's equation, was equal to negative some factor times the function. And so if it was the second derivative was proportional to with a positive coefficient, right, then that is going to be, that's going to be just a regular real exponential. And if the second derivative is proportional with a negative coefficient, it's proportional to the original function with a negative coefficient, then that's going to be, what you take, it's going to be an imaginary exponent. And the imaginary exponent gives a cosine or sine. That gives you the oscillated term. So anyways, it's all coming together in some ways. Here what we're going to do is we're going to, instead of taking a discrete sum, we're taking a sum over a continuum, an integral. And instead of having a whole bunch of separate waves, each with their own amplitude, we're going to do these things right here. We're going to have a continuum of waves. And so their amplitude is going to be a function of the thing that's forming the continuum. In this case, what forms the continuum is that wave number. And one thing I want to point out right here, you're like, that looks pretty simple, except it turns out that this omega right here varies with k. Yes, this should be complex. Yes, I believe it should be. It's not going to make sense otherwise. Is that right? Yeah. And again, right, our k goes from minus infinity to plus infinity. Those are the bounds. And you take a look at this, and what does it mean to have a negative wave number? Well, that's like remember the wave number k is 2 pi over lambda. So first of all, a negative wave number is, if a positive wave number will be a wave going to the right, negative wave number will be a wave going to the left, right? So it indicates the direction that they're going. And then when k is 0, so what gives you 0, that's going to give you an infinite wavelength, something really, really broad. When k is gets really, really big, then 2 pi, or something really, really big is 2 pi over something small. So a very large k corresponds to a very short wavelength. Lots of oscillations. And so these Fourier transforms are going to be really, really useful to us. And I'm going to watch for this last 3 minutes. Let's just talk about kind of in general what the properties of Fourier transforms are. And so here, let's make a column here, Z, and here what it looks like in K. So something that is broad in Z is going to look like a delta function, so in K. Right? So something that's got a really super long wavelength is a delta function at 0 for K. Right? Something that, and this is centered at 0, right there. Right? Something that is a pure cosine or pure sine, that's going to correspond to, well, here's my 0. You're going to have a delta function at 2 pi over lambda and minus 2 pi over lambda. Right? Because if you just take a snapshot and look at just the picture of this cosine, this could be something with a certain wave number k that's going right or to the left. We can't tell just from a snapshot. Or if this is actually just standing still like this, that's because there are left and right ones counter propagating, left and right word moving waves. Counter propagating, you get the standing wave. What else? Oh, and similarly, if you have a delta function is going to turn into something, the Fourier transform of that is something that is really, really broad. Right? Because, all right, one way to think of it is, how do you make a delta function out of cosines and sines, right? Well, one way to do that is you add together a bunch of cosines, and you start out with them being, actually, let's go back to the pen, right? You add together a bunch of cosines. Well, you have some that are some that's just kind of going like this, and then some others that are going faster oscillations that partly cancel that out. But notice right here, they're all adding together right here in the middle. And we do some that are even faster oscillations. So overall, if you add together all the different cosines possible, everywhere you go, you're gonna have positives or negatives, except right at 0. They're all +1. So you get, what you end up with is a delta function. They all add constructively at 0 and average out, and they're 0 everywhere else. So just very, very generally, that relationship between lambda, between our wavelength in Z, and K, our spatial frequency, the wave number, is something that is broad spatially, will have a narrow spread of wave numbers. That's supposed to be an O. And something that is narrow will have a broad spread of wave numbers. In order to have kind of the sharp parts of something, to make up something narrow, you've got to have some pretty short wavelengths. So that means some pretty high wave numbers to do that. Other interesting things, if you've got something that's made up of a bunch of delta functions regularly spaced, like a comb, train of pulses, the Fourier transform of that, well, okay, it's kind of like having a really broad spread, so it'll give you spikes, but it's kind of like having spikes, so it'll give you a broad spread. So the Fourier transform of a comb of delta functions is a comb of delta functions, right? They're both broad in terms of the whole comb, but it's narrow, each one of the spikes. What does a delta function mean where? Sorry, did my video just get bad? And we're just short of ending. The delta function is either, so here this is a bunch of pulses as we go along in our wave, and that corresponds to having a bunch of discrete frequencies, right? Because this is both broad space, but also each one of them is narrow in space. So we need something that is narrow in wavelength, but also broad, narrow in wave number, but also broad in wave number. So I'm kind of just giving you a hand-waving explanation, but the real explanation is, of course, this equation right up there. So last couple things, the Fourier transform of a Gaussian. Gaussian is a Gaussian. I don't know why one was capital and one wasn't. And I ran out of space. Here's something interesting. I ran out of space in Z. If you have something that oscillates but decays, that exponential that was both real and imaginary, I'm going over here. And what this turns out to be is a different kind of peak form called a Lorentzian. So if you have oscillations that decay away, then what you get is a peak. So when we learn about transitions in atomic physics, right, and we say, oh, there's just one frequency. Well, the transitions, you can think of it as an oscillating dipole that decays away as you make the transition. If you have a whole bunch of atoms, the transitions have some finite line width right here. Same thing in a mechanical oscillator, right? It doesn't have just one resonant frequency because the oscillations actually damp out. So what we get is kind of a band of frequencies. So Fourier transform, notice we're talking about this here in E&M, but we just dropped in references to quantum mechanics, to classical mechanics. Really, really super useful. This is one of these unifying tools across the board. So I'm going to snapshot this too, and we'll, on Monday, actually take a look at waves and what happens when they hit things. It's the beginnings of optics. So no homework, no assignments, nothing deliverable for Monday, but go ahead and do start in on the homework, please. Awesome. Sorry for running over again. Just again, it takes time for me to get used to how slow stuff is. See you all on Monday. Cool. Yep, see you all shortly. Oh, forgot about that. Yes. See you shortly. 25 minutes. I'm going to send her an email about that. Yay.